about what one speaks. Yeah.
Yes, sir. And it is about to live in a fraction of seconds.
Okay.
Yeah.
Go to next slide.
Yeah, we are live now. This is
Okay,
just for
so
the information.
yeah.
Yes, Punita ma'am, please carry on.
Yeah, please. So welcome everybody to this another evening of learning physics with conceptual and problem-based approach, organized by the National Academy of Sciences India, NASI Delhi chapter, under the chairmanship of Professor Ajoy Khatak, who is the most respected teacher everywhere around us. And it's a 10-week course started on 27th of July, 2020. We are blessed to have Professor Ajoy Khatak's presence today evening with us. May I request you to have a next slide, please? Today we are going to have two lectures. The first lecture would be on classical mechanics by Professor R Seshadri from the Department of Physics and Astrophysics, University of Delhi. And the second one on electricity and magnetism by Dr. Sudha Gulati from Kalindi College, University of Delhi. Next slide, please. So here I would now request my co-convener, Dr. Pushpa Bindal, to kindly introduce the speaker, Professor R Seshadri, to our audience. Thank you.
Thank you, Dr. Pushpa. It is a pleasure to introduce Professor R Seshadri to the participants. Professor R Seshadri is presently working as a professor in the Department of Physics and Astrophysics, University of Delhi. He completed his 5-year MS from IIT Delhi in 1983 and his PhD from TIFR in 1989. He has done his postdoc at CSIR RA at Delhi University and has been a Nehru Centenary Fellow at University of Sussex, Brighton, UK. He was also a postdoc fellow at Physical Research Laboratory. He started his career from Harish Chandra Research Institute, Allahabad in 1992 and joined the Physics and Astrophysics.
Keep your mic closer.
Excuse me,
Ma'am,
ma'am.
will you please speak closer and remove those earphones? It's not clear.
Yes, ma'am.
Oh. Is it better now?
Yes, ma'am. This is better.
Yes.
Okay. So I'm sorry.
Yes.
I would like to start again. I would like to introduce Professor R Seshadri to you, to all the participants and to the panelists. Professor R Seshadri is presently working as a professor in the Department of Physics and Astrophysics, University of Delhi. He completed his 5-year MS from IIT Delhi in 1983 and his PhD from TIFR in 1989. He has done his postdoc as CSIR RA at Delhi University and has been a Nehru Centenary Fellow at University of Sussex, Brighton, UK. He has also been a postdoc fellow at Physical Research Laboratory. He started his career from Harish Chandra Research Institute, Allahabad in 1992 and joined Department of Physics and Astrophysics in 2001. He has been teaching classical mechanics, quantum mechanics, astronomy, astrophysics, and general theory of relativity. His research interests include working on large-scale structure in the universe, cosmic microwave, background radiation, astrophysical and cosmological magnetic field, early universe, late time acceleration in the universe. He has published several research papers in the reputed refereed journals and also presented his work in many national and international conferences. So, Professor Seshadri, we welcome you very warmly, sir, and we request you to share your expertise with the participants. Thank you.
Thanks a lot. Hi, Professor Khatak. So nice to see you. I still remember your quantum mechanics classes. Okay, so the problem with giving such a flowery introduction is that one is under tremendous pressure to stand up to it. Okay? So let me see what we done. So can we have the first slide? So how does it work? Are you going to project it?
Yes. So Dr. Poonam, are you going to display the slides?
You mailed it to me?
Yes, to you.
Just a minute, ma'am. I was sharing the screen. I was not able to access my mails.
Okay.
Just give me
So,
1 minute.
yeah. Professor Seshadri, what are you going to teach us today?
Okay, so I will start with some basic philosophy of Lagrangian mechanics. Okay, I mean, how is it different and how is it similar to standard Newtonian mechanics? And then I will go over to the equation for the extremum path, and then connect it up with Newtonian mechanics. And also why the Lagrangian for mechanics is kinetic energy minus potential energy. Then I will start with some simple one-dimensional problem and tell how to solve it. I mean, it may actually, I am expecting that there'll be a wide spectrum of people who are attending. So for some of them, it will be trivial and some of them, it will be okay. So I think, I request patience from those who feel it is trivial. Okay, and then I will go over to why is the need for approximate methods and computational approach to solve them. And then I will tell about the fact that Lagrangian is not unique, and there is certain freedom in choice of Lagrangian. And I will give some examples of how the same equations of motion come about. And then I will talk about, from the mathematical structure of Lagrangian technique, how it can be used for solving problems in other areas. And as an example, I will take the case of the shape of a soap film and map this problem to the Lagrangian mechanics problem, use the Lagrangian equations to get the equation for the surface of a soap film. So this is what I have in mind right now. And so I am going to have 1 hour or 1.5 hours or something, right?
Just
Yes,
a minute.
yes, yes.
Just a minute.
So Poonam, so if you require whiteboard, you have to just say that you require whiteboard, and then that will be also shared to write.
I agree. Okay, fantastic. Yeah, okay. I require whiteboard. Okay, let us see.
So, Dr. Poonam, make Professor Seshadri the co-host.
Can you just check here? Yeah.
Yes, ma'am. I will do that. Ma'am, actually, it is getting downloaded because I think it is a heavy file. Just give me 1 minute.
Punita?
Yes.
We can do one thing. After this is over, sometime later today, we can just try out how to do this. I think there is something which I'm missing.
It's not a problem. Definitely we'll do that.
Yeah.
It was not expected. Yeah. Otherwise, generally we do it always beforehand also. So it's,
because usually what happens, I have this 12 o'clock session, 12 noon session with all my students, and I just very trivially do it. So I never thought that would be a problem.
Downloaded, Poonam? Yes, no?
Yes, ma'am. I'm sharing the screen now.
Okay, fine. So you will say next slide or you will say whiteboard, and that will be shared with you, right?
Okay.
Sorry for the trouble, and I'm sorry also to the participants.
I should have tried it out earlier.
I think it is visible to you, sir, and
yes.
everyone.
Yeah. Yes. Yes.
Okay.
Yes.
Increase the size, Dr. Poonam. Increase the size. Zoom it.
Just a minute.
Okay.
Right panel has to be removed.
1 second. Ma'am, if I am making it full screen, then size will be reduced. And if I am making the size a little bigger, so then it is not full screen.
So you'll have to scroll it down, up and down. It's in
no problem, no problem.
So just increase because it's too small to be seen even on a computer.
Okay, so ma'am, I will
like this and remove the right bar.
Yeah, this is
remove the right bar.
Now it is fine.
Yeah, okay.
Okay.
Yeah. And then you have to scroll up and down.
We can scroll down. That's not a problem. Yeah.
Yes. So it will be ensured that Poonam is listening very attentively.
Yes, sir.
Okay.
Yes, sir, I will do that. Yes.
Fine. Okay.
Revision.
So welcome everybody. So I can only say I will attempt to tell you how to solve classical mechanics problem through classical mechanics through problem solving. Now, first of all, in mechanics, what is it that we are aiming for? We are basically aiming for to find out that if suppose you are given a set of forces, then under the influence of the forces, what is the trajectory taken by the particle, which we call classical paths. Now, since all of you must have also been introduced to quantum mechanics, I will just very briefly mention where exactly the difference lies before I go over to classical mechanics. In quantum mechanics, there is no distinct path. There is nothing called the trajectory. In principle, the particle, in principle, can follow any trajectory, and then we have. Yes, there was a hand. Yeah. Yes, please.
The hand is most of the time a mistake by them. If they have to ask a question, they have to put it in Q&A. So they.
Okay.
The hands we cannot see. They just press the hand just like that.
Oh, I see. Okay. So in quantum mechanics, you don't have a unique path. There are all possible paths. And then, as we know, I mean, you have the wave evolution along different paths. We do the interference among all of them, and we see what is the probability of getting, finding a particle at a particular point at a future time. However, among all the paths, okay. So fine. So now, then the value of h cross becomes smaller and smaller. Then the highest probability of the path is around the path which is the classical path. And so, in the transition from quantum mechanics to classical mechanics, one can broadly say that when h cross goes to 0, all the other paths, the probability dies down very fast, except for the thing around the classical path. So, so in classical mechanics, we will not be talking of all the paths, but the unique path taken by the particle in the limit of h cross going to 0. Now, there are two ways of approaching mechanics. They are actually similar, but I will tell you what is the difference on the face of it. The first is the approach which one has been used right from school onwards, which is the approach by Newton's laws of motion. And in this, and there is another approach which is called via action principle. Now, are these two approaches independent? The answer is no. Although on the face of it, one may think mistakenly that the Lagrangian approach is in some sense more fundamental than the Newtonian one. Now, what happens in the first approach? We have Newton's second law, which we have mx double dot equal to the force. Now, this is a differential equation. It's a second order linear differential equation. In order to get the solutions, I need two conditions. So, for example, if I put the initial conditions, then I can solve for x as a function of t. Now, how did Newton formulate his laws? Newton formulated his laws purely from observation. He constructed the laws such that these laws can produce the trajectory of the particles which we observe in nature. So Newton's laws were in some sense just a mathematical formulation, direct mathematical formulation of the way particles behave under different force fields. Now, there is a second approach which we call the action principle. Now, in action principle, what we do is we first construct a function. Now, you can ask, what function do we construct? I will shortly come to that. We first construct a function called a Lagrangian. And this function is a function of, I see that I have done a mistake. Unfortunately, I can't correct it here. There should be a dot on top of the second q. Okay. So there is this Lagrangian, which is a function of q dot, which is dq by dt, and time. So what it means is, this Lagrangian, the value, sorry, what was that question? I mean, some chat message had come. Oh.
Palak Naz and Vikyat Sharma, if you have a problem, write it down there in the chat box or in the question answer box. Please don't raise hands. Yeah, sorry, please continue.
No. Okay. So what happens is, this Lagrangian is a function. Now, it is not a function, or it is not a given just a function of the position in space. Not only it depends on what is the position of the particle at a particular time, it also depends on with what velocity the particle is moving at that point. So that's why it's a function both of q as well as q dot. Q dot is dq by dt. And then we construct an animal called action, which is an integral of this Lagrangian from an initial point q1 at a time t1 till a final point q2 at a time t2. And this integral is done along a certain path of q versus t. So this s does not only depend on the starting point and the end point, but also what path the particle takes. So if I take any, so what path the particle can possibly take. Okay, and the path is basically defined as q of t. Now, there is a subtlety which I want to point out here. See, the q which appears in the Lagrangian is not the actual path taken by the particle. Q is one of the possible paths which can be taken by the particle. And when I do the action principle, it will identify one of those paths, and that is actually the classical path, which I call QP. So Q of t is a general path, QP is a particular path taken by the particle. Now, this QP path is that path taken by the particle for which this integral is a minimum, or more strictly an extremum. So this is the action principle, that is the actual path taken by the particle is that for which this integral is an extremum. Okay. Now, one can now ask the question, how do I decide what is this Lagrangian function? I could say there's a Lagrangian function, I can do it. So that is the catch. The catch is in determining L as a function of q dot nt. Now, different L's will give me different paths for the minimum S. Then I can ask, what is the correct L? The correct L is that L for which the path given by minimizing the action is actually the classical path taken by the particle, or in other words, one which follows Newton's laws of motion. So ultimately, so how did Newton's laws of motion were obtained? That is from experiments and observations. So in other words, even in the Lagrangian approach, the Lagrangian, which is the correct Lagrangian, is the one which gives the correct observed path of particles. So in other words, this is the answer to the question which I asked earlier. Are these two independent approaches? The answer is, strictly speaking, no. Because whether you are doing it through Newton's laws or you are deciding what Lagrangian to choose, both these are governed by observations. Because, see, given any Lagrangian, of course, I can take some paths, but nature has no obligation to follow whatever mathematical law we formulate. If I have one Lagrangian, there is a certain law of how the particle moves. Another Lagrangian, another law as to how the particle moves. Now the question is, which Lagrangian should I choose? That Lagrangian which nature follows. So the nature has no obligation to follow whatever mathematical law we formulate. Now, so to understand nature, the laws of nature, it is ultimately based on experiments and observations. And that is why one should remember always that physics ultimately is an experimental subject. The theory may give a way of understanding the process, but ultimately whether the truth of the theory or the validity of the theory purely hinges on the fact that whether it produces the observed universe, the observed phenomena or not. Okay, next slide. Okay, now let us go to this thing about the equation for extremum path. So as I said, so here I have this Lagrangian, which is a function of q dot and t, the integral dt, t1 q1 to t2 q2, and it is assumed that this integral is over a certain path. Now, now I will not go into the derivation of Lagrangian equation of motion because this is the standard thing which is done. What I will say is, given an L, I have this machinery called the Lagrangian equations of motion, in which you have d by dt of del L by del Q dot equal to del L by del Q. And if I choose the correct Lagrangian, when I say correct Lagrangian, the Lagrangian which reproduces the natural phenomena which we observe, then we land up in Newtonian equations of motion. Now, yeah. So for example, suppose I take the Lagrangian, which is on the left-hand side. The Lagrangian is half m q dot square minus v of q, the potential which is a function of q, or at present it is some function of q. Now I put this into this machinery of Lagrangian equations, del L by del Q dot, it is mq dot, d by dt of del L by del Q dot, which is mq double dot, and if I equate it to del L by del Q, I get the familiar equation of motion, which is mq double dot equal to minus gradient of v. Now this, as we see, is consistent with Newton's laws of motion, and that is what we observe in nature. Now I can ask another question. I have said Q1 and Q2. Yes, there is a, sir, you have written Q1, Q2 in the integral limit because of the fixed points or another reason? Yes, that's right. It's because of the fixed point. Because I know that the particle was located at Q1 at time T1, and it reaches Q2 at time T2. So I am fixing these two. That's correct. How Newtonian mechanics and Lagrangian mechanics are not independent. Okay. Punita, can I just answer it straight away instead of typing it in or something? I mean, it says type answer.
Yes, no, you don't have to type. You just answer it.
Okay.
If you feel like answering in between, it's up to you.
Yeah,
at the end, it's up to you.
No. So, okay. So I will just repeat it. The question which somebody has asked is, explain how Newtonian mechanics and Lagrangian mechanics are not independent. See, as I said, in Newtonian mechanics, the observations and experiments play a direct role. Newton observed that things move in a certain way. He constructed a mathematical jugaad. What is the dimension of action? I'll just complete. He constructed a mathematical jugaad, and then he said that this should work. And it so happens that it works. That is, so there is nothing called deriving the Newtonian equation. That one should remember. You know, often people, in fact, I know actually some exams in which they ask, say, derive the Schrodinger equation. There is nothing like that. Newton's laws or Maxwell's laws or Schrodinger equations are not derived. They are at best motivated. Okay, so Newtonian equations of motion are only motivated by observation. So they're directly from observation. Now, what happens in Lagrangian? In Lagrangian, as I said, you choose a function, but nobody tells you what function to choose. You can ask the question, how do I choose the function? The answer is, I choose such a function such that the Lagrangian equation of motion gives me the Newtonian laws of motion. So, since there is no basic principle, there are some very basic some principles by which you can narrow down what is a Lagrangian, but it does not give a unique Lagrangian. Okay, so it means that the choice of the Lagrangian is dependent on what laws of motion it produces, and that is why Newton's mechanics and Lagrangian approach are not independent. Is that clear? Okay, I assume it's clear. If it is not, I will assume that people will tell. Okay. Okay, then another question is, what are the dimensions of action?
Clear. It is clear.
There is a delay. There is a delay of a few fraction of seconds by the time yes will start appearing.
That's okay. That's okay. That's okay. That's okay. Okay. So now another question: what are the dimensions of action? Dimension of action is basically energy into time. It is actually the dimensions of Planck constant. The dimensions of action. That is why, I mean, if people have done path integral, then in the exponential you have e to the power action by h cross. So it has the dimensions of h cross, which you can say angular momentum or energy into time or whatever. Okay. Another question is there a unique Lagrangian function for every classical problem so that it follows Newton's law? Okay. Now that is the one which I am coming to. That is, I will be coming to it. That is how much freedom you have in the choice of Lagrangian. Okay. In fact, to give you the immediate answer, the choice of Lagrangian will not be unique. One example is potential. You know, if suppose I add a constant term to the potential, the equations of motions don't change. So that's a very trivial example of why it is not unique. But now I'll come to the details. Okay. So now I said that suppose I use, instead of this Lagrangian, I use the Lagrangian which I have given on the right hand side in purple. Now, you forget about the fact, where did I get the Lagrangian from? That's a different matter. But if I am given this Lagrangian, I can put it in the equation of the Lagrangian equation of motion and get an equation which I have written in the bottom in purple, which is mq double dot equal to mq dot square by q minus, I have a Lagrangian and I have got the got an equation of motion. Now, okay, so now, should I accept this Lagrangian? On what basis will I say whether or not I should accept this Lagrangian? I cannot accept this Lagrangian for the simple fact that it is not consistent with Newton's laws of motion and hence not consistent with what we observe in nature. Now, this is again the answer to that first question, that how do you say that Newton's equations and Lagrangian equations are not independent? Ultimate test of whether the Lagrangian is right or wrong is dependent on whether it can produce Newton's laws or not. Okay. Now, if you look at the left-hand side, which is actually the Lagrangian for a particle moving in one dimension, we recognize that from the equation, the last equation, the right-hand side is a gradient of something. Now, we know from Newtonian mechanics that mass into acceleration, which is the left-hand side, is the gradient of potential energy. So, which means that this VQ is the potential energy, and the other term we know is our familiar kinetic energy. And that is why, in order to produce Newton's laws in mechanics, the Lagrangian described, Lagrangian is given by kinetic energy minus potential energy. Okay, it's kinetic energy minus potential energy. Okay, fine. So because often the Lagrangian is introduced as kinetic energy minus potential energy by some kind of a magic wand. So this is it. Now let us go to a bit of problem solving. Okay. Now here I have just some arbitrary one-dimensional potential. I have got V naught, X naught by X. I put all these constants so that, to match the dimensions and so on. Exponential minus X by X naught. And given this potential, now, since now I am enlightened by the fact that for mechanics, I need to have the Lagrangian as T minus V. I write the Lagrangian as half mx dot square minus V naught X naught by X e to the power minus X by X naught, which is the potential. And I calculate del L by del Q dot. Okay, after this is over, I think I will say a few things about partial derivatives and total derivatives, because it's used a lot here and often there is a confusion. So I will give you a physical interpretation of these. So here I have del L by del Q dot, which means that when I take this derivative, the other two variables Q and T I freeze. And that is equal to, if I apply on this Lagrangian, is mx dot. Similarly, d by dt of del L by del Q dot is mx double dot. And the right-hand side of the Lagrangian equation is del L by del Q, which is basically, if I take the gradient, what I get in the right-hand side, V naught by X into 1 plus X naught by X e to the power minus X by X naught. I dump it into the Lagrangian equation of motion, and there I get the Newtonian equation of motion. Well, what I have achieved is basically the point from where we usually start in undergraduate physics. All what I have told you is in the first, initially it may look like a very convoluted way of stating the same Newton's laws which we have always been doing. Okay, but this has its own advantages. Now, what we observe with this law is the following: that is first a second order differential equation, and hence it needs, I should be TWO2. It needs two conditions. It could be initial conditions, it could be conditions at two different points, or it can, for example, it can be X dot and X at some time T and so on. So once I do that, in principle, this can be solved. However, the equation which I have just given cannot be solved analytically. It turns out that there is a very limited and a small class of problems in physics which can be solved analytically. And that is why, if you go to a biologist or zoologist and discuss something, he will soon come out with, consider a rabbit or something. Similarly, if you talk to a physics about mechanics, very soon he will say, let us assume a simple harmonic oscillator. That is because simple harmonic oscillator is one of the very few exactly solvable problems. So, in most cases of physical interest, although the differential equation can be formulated easily, as we have done, the exact analytical solutions is not possible in general. And this is the importance of approximate methods and computational approach. I will not go into these, but one should not go back with the impression that since you have formulated the Lagrangian equation, everything is done. The problem has only begun. All what I have done is, I have put it in a mathematically concise formulation as to what is the problem to be solved. Now I come to this question, is Lagrangian unique? The simple answer is no. But that is not sufficient. It is like, you are going somewhere and one person asks, can you tell me the time? And the other says, yes. So when you say, can you tell me the time? You are expected that the time is so and so, and not just whether you can or cannot. So now, the answer of is Lagrangian for a system unique? The answer is no, but that is not sufficient. One has to now look at why it is not unique. So now we come to the freedom in the choice of Lagrangian. There is now I am already equipped with the thing that for mechanics, the Lagrangian is given by kinetic energy minus potential energy. And I also know that to the potential energy, if I add a constant term, nothing changes. Okay, sorry, there is a question which I missed. Please explain why kinetic energy. Okay, the simple answer is the following, and that is the answer. In mechanics, unless I choose the Lagrangian as kinetic energy minus potential energy, I cannot reproduce Newton's laws of motion from Lagrangian equations. That is the honest answer to this. As I keep repeating and I keep emphasizing, I'm a theoretical physicist, but I keep saying that physics is ultimately an experimental subject. Theory can only explain, try to explain why things happen the way they happen. Okay, so ultimately you need to construct the Lagrangian which produces the experimentally observed result, which is Newton's second law. So the Lagrangian being kinetic energy minus potential energy, its construction is purely because that is what gives you the Newton's laws of motion. As I earlier showed, I used a slightly different Lagrangian, and we saw that this was not giving Newton's laws of motion. And this is the way to say that that is not the appropriate Lagrangian. So in fact, although I have used the word correct Lagrangian, it is a misnomer. The right word is the appropriate Lagrangian, because there is not, Lagrangian has nothing to do with correct or not correct. Lagrangian is a function. In order to apply it for something, we have to choose the appropriate Lagrangian. The appropriate Lagrangian for mechanics is kinetic energy minus potential energy. I hope that is okay, Ishita. Okay, so now, as I was saying, in the freedom of choice of Lagrangian, see, we saw that Lagrangian is kinetic energy minus potential energy, and I also know that if I change the potential energy by a constant value, we know that the equations of motion don't change. And that we know because the equations of motion involve gradient of the potential, and if there's a constant term added to the potential, there's nothing which happens to the gradient. Okay, so already we see that there is this simple freedom available. But more generally, one can see the following. See, the Lagrangian equation does not involve purely the value of the Lagrangian. It involves only derivative of the Lagrangian. And when there is a function and I take its derivative, I am actually losing some information, which means the equations of motion do not require the full information in the Lagrangian, but only a partial information to the extent to which the derivative of the Lagrangian will be affected. And as I said, one trivial example is addition of a constant to the potential. But this is not all. There is more to it. Now, in order to see that, let us consider two Lagrangians. One Lagrangian, which is a general Lagrangian, some L, Q, Q dot, comma T, and I construct another function, L prime equal to L plus, I have a function which is F, which is a function only of Q and of T. And I take the total derivative of this function. Now, I will, okay, can I have the whiteboard?
Yes, sir. If you
can I have the whiteboard for
yes,
some
sir.
time? I want to explain something.
Sir, you need to share the screen. There you have the option of whiteboard.
This is what I am saying. When I am a co-host or something, that doesn't appear here.
Whiteboard is not appearing.
You see, that's what I'm finding surprising, because when I have been the host, when I usually do these things,
yes,
then
sir.
Obviously whiteboard, everything appears, I have no problem. So that's what I was assuming.
Okay.
Okay, so fine. So I will just describe it in words then. There's no other way of. Okay, Punita and I will try to figure out later today as to what to do. Okay. So I go to the person who is sitting on the raft. Now, this person has already also thrust a thermometer inside the water. But now, what is he doing? In his case, neither the time is static nor the space is static. Both are flowing. Now, so when he measures the temperature, what he does is the following. Suppose there is a small packet of water around the raft. As the raft flows, the thermometer records the temperature of the same packet, unlike the person on the bank of the river, where the person's position was fixed. So, with time, the temperature being recorded was not the same packet of water, but as the water flows, different packets of water was recording some temperature. And the person on the raft, here, what this person has fixed is the packet of water whose temperature he is measuring. But in his case, neither the time is static nor the space is static. The temperature, the rate of change of temperature, which is measured by the person on the raft, is d temperature by dt. So, the difference between the temperature measured by the person on the raft and the temperature measured by the person on the banks is basically that while the person in the bank is measuring temperature not of the same packet of water, but is measuring the temperature at the same position in space, irrespective of what packet comes there, the person on the raft is measuring the temperature of the same packet irrespective of what position is located in. The one which the person measures on the raft is the total derivative d by dt, and the thing which the person measures on the bank is del by del t. That is the physical difference between these two derivatives. Is it okay? So since Punita knows the students well, she can tell me if this is likely to have made things clear. Okay, Punita has vanished. Okay, fine.
Yeah,
fine.
yeah.
So I have got something.
Time delay. No. Time delay in switching on and the voice reading.
Sir, one of the participants, Samarine, is saying, please repeat the last sentence.
Okay. Please let me think what was the last sentence. Okay. So okay. So let me tell you what I think was the last sentence. If it is not, then you can ask me. You already heard that. Okay, the person who is sitting on the bank of the river, for this person, the thermometer which he uses, the thermometer's location is fixed, but not the packet whose temperature the thermometer is measuring. As the river flows, different packets keep coming and recording the temperature on the thermometer. Whereas the person who is sitting on the raft, for that person, the thermometer is measuring the same packet which is flowing with the raft. But what is not fixed for this person is the position where that packet is kept. The thing which is measured by the person on the bank is the partial derivative of temperature with respect to time. The one which is measured by the person on the raft is the total derivative with respect to time. So I suppose this was the last sentence. Okay. Fine. So this was an aside on partial derivative. And so I wanted to tell this because here I am using, there is a change from L to L prime. L to L prime, L to L prime. Can you go up, down, side? Yeah. So L prime is defined as a total derivative of a function of position and time added to this Lagrangian. So now we have two Lagrangians. One is one Lagrangian. Given any Lagrangian, I can construct another function L prime, which is given by this. Now f can be any function. Only constraint is that it should be a function only of position and time, not of velocity. So now, since now we come to that partial. So now d by dt of f, as I said, as in the case of the measuring temperature of water, the thing which the person on the bank measures, the change in temperature, is a combination of the change in temperature of an individual packet plus what packet comes. So there are two components to it. And so the total derivative, just a minute. Computer has gone to sleep. I think the computer is feeling bored of my lecture. Yeah, so now this df by dt, I can write as del f by del q, q dot, plus del f by del t. It's actually del f by del t, dt by dt, dt by dt is 1, so it is just del f by del t. And so now what I do is, let me assume that L prime is another Lagrangian, and let me, so as I had told, given any Lagrangian, I can write the Lagrangian equation of motion. Whether it describes nature or not is a different issue. So given this Lagrangian L prime, let me write the Lagrangian equation of motion. So I have del L prime by del Q, and this, when I apply it on this equation, is del L by del Q plus, now Q dot is independent of Q. Okay, this I think I should mention. You see, okay, I should mention this. You see, often this confusion is there when people do Lagrangian mechanics. They say that, if my trajectory is given, the slope of the trajectory is also given. So why is Q dot independent of Q? The answer to this is a very interesting subtlety. At the level of Lagrangian, you have not yet chosen the equation of motion. At the level, so let me give an analogy. Suppose I have a desert, and in the desert, I have drawn a large x-axis and a y-axis. Now the x-axis, the x-axis of a point is independent of the y-axis. Given a point, I can choose an x-coordinate, and whatever with the x-coordinate, I can choose whatever y-coordinate I choose. I can always point it. So the coordinate y and the coordinate x are independent. Whereas, suppose in this desert, a truck has passed. So it has made a path on that. Now, what is the path? If I give a function of what is the function of y as a function of x, it will give me the path. So x is a function of y once I choose a given path. So, and which I call a trajectory. So in a trajectory, x is a function of y, or y is a function of x, but the coordinate y is not a function of coordinate x. If I choose that for every x, this is the coordinate y, then I have defined a path. In a very similar way, at the level of the Lagrangian, q and q dot are like x and y. For every q, I can have any q dot, because I have not yet frozen what is the actual path taken by the particle. Just like I have not chosen in the desert what is the path taken by the truck. Once I solve the Lagrangian equation, it gives me a unique path. That is, it gives me a certain function of q and q dot, which tells me that this is the classical path. Just like in the case of the truck in the desert, once the truck has passed, the relationship between y and x tells me defines what is the path taken by the truck. So it means that at the level of Lagrangian, q and q dot are like coordinates. They are not like the trajectory of a particle. You have to be very careful about what is the trajectory of a particle and what is the coordinate. The coordinates are independent of each other. So for any q, I can take any q dot. And that is why in taking this partial derivative in del L prime by del q equal to del L by del q plus this, when we say del by del q, q dot gracefully comes out of the derivative because it is not a function of q. And so I have del 2f by del q square times q dot. And then, but f is a function of q. So it have del 2f by del q del t. And now I simplify this. No, sorry. What I do is, this is my right-hand side of the Lagrangian equation. Now I go to the left-hand side. Left-hand side first involves its derivative with respect to q dot. So I have del L prime by del q dot equal to del L by del q dot plus. Now in this, I told you that f is a function only of q and t. So del f by del q is a function of only of q and t, not q dot. So here, del f by del q behaves as a constant as far as derivative with respect to q dot is concerned. And since q dot is a linear thing there, so I have just del f by del q. Del q dot by del q dot is 1. So I have del L by del q dot plus del f by del q. And now what I do in the left-hand side of Lagrangian equation, I take a d by dt. So I have d by dt of del L prime by del q dot is equal to d by dt of del L by del q dot plus d by dt of del f by del q. Remember that this is a d by dt. It is not del by del t. And so in the next step, I will expand del by del t of del f by del q as, suppose I call del f by del q as g, then it will be del g by del q q dot plus del g by del t. If I put g as del f by del q, I have got del 2f by del q square q dot plus del 2f by del t del q. So now I compare these two, what I have shown the arrow there. So what happens? Here, I mean, the f is a nice, well-behaved analytical function. So the order of derivative does not matter. So del 2f by del q del t is same as del 2f by del t del q. Similarly, del 2f by del q square q dot is also here. So the second and third term on the right-hand side for both the equations which I am comparing is the same. Now, I know that L is a legitimate, honest-to-God Lagrangian, which means that it follows the Lagrangian equation of motion. That means del L by del Q, which is the first term on the right-hand side of the first equation, is equal to d by dt of del L by del Q dot, which is the first equation of the right-hand side of the second equation. It means that the right-hand side is same both these equations, which means I immediately have, as I've written in green below, del L prime by del Q equal to d by dt del L prime by del Q dot, which is also the same Lagrangian equation of motion, which means that if I add a function of the type d by dt of f of q and t, although the Lagrangian changes, the equations of motion remain the same. Now this, I think, would have answered one question which was asked about the uniqueness of the Lagrangian. Is this clear?
Yes, sir. This was asked by Pranjali Sharma. If she is here, can you please respond, Pranjali Sharma? Is it clear to you? Okay, sir. I will tell you if she writes in the chat box.
Yeah.
You may continue. Thank you, sir.
Now, okay. Now, usually this derivation is given in a different way. Landau and Lifshitz, which is my favorite book. Can you repeat the del f by? What was that? Can you repeat the del f by del q step? Del f by del q step. Okay. Okay. So I presume it is. No, Samiran, I am not able to understand from which point.
Samiran, can you please elaborate your question?
There are so many del f and del q.
Yes.
Yes.
So exactly. So the first, whatever is equation now.
Scroll up
a little.
Scroll up a little.
Okay.
Scroll up a little.
Okay. Is it fine?
You start, yeah.
Oh, this one. Okay. This is nothing. I mean, so it is a standard expression for the total derivative in terms of partial derivative. So if f is a function of x and t, then d of f is equal to del f by del x dx plus del f by del y dy. Now here, suppose I want to find out del df by dy, then that after del f by del x, you have dx by dy, and then plus you have dy by dy. So only del f by del y survives. So that is why it is the d by dt of f is del f by del q dq by dt plus del f by del t. Since it is a function only of q and t. I just hope it is clear
Yes,
from
sir.
Samir and okay, sir. Thank you. Okay, fine. Okay. So usually what happens is there is a simpler way thing, but I didn't want to do it. Basically, what it says is, if I use this Lagrangian and vary this Lagrangian while deriving the Lagrangian equation of motion, then this addition of this term will only affect the endpoints, and since the endpoint variation is 0, it doesn't affect the equation of motion. But I thought for a more transparent understanding, I thought this may be an explicit solution may be better. So the moral of the story is, if for a system L is a Lagrangian, for the same system L prime is also a Lagrangian, provided L prime can be expressed as L plus d by dt of any function of q comma t. So this is the moral of the story. Okay. Now we'll come to some example. Next slide. Okay. Now, so let us take, as I said, however much theoretical physicists may say about solving problems, there are only very few problems which can be solved exactly. And one of them is this one, simple harmonic oscillation. Okay. So now let us consider the Lagrangian half m square half m x dot square minus half k x square. It's a standard simple harmonic oscillator Lagrangian. K is the force constant, m is the mass, and x is the potential, one dimensional. Now this is from Kleppner-Kolenko. Oh, acha, Kleppner-Kolenko does it this way, is it? I didn't know that. Okay. I only seen Landau-Lipschitz where actually he does it right at the time, at the level of deriving the Lagrangian equation of motion itself. Now, what I do is the following. To this Lagrange, so I want to define a new Lagrangian. And the new Lagrangian I define is, I just add a term x dot t plus x. Now the question is it a form of d by dt of a function of qt? Indeed it is, because I can write it as half m x dot square minus k x square plus d by dt of x into t. So my function f, which is q comma t, is now x into t here. And so I have written it exactly in that form, and I expect that the same equation of motion will be there, because they differ only by this kind of thing, d by dt of f of q comma t. So I expect the same equation of motion, and let us demonstrate that it is indeed true. So I have with L, I have the Lagrangian equation of motion. Del L by del x is minus kx. D by dt of del L by del x dot is mx double dot. And I put in the Lagrangian equation of motion, which is mx double dot equal to minus kx. Let us now go to the L prime. Del L prime by del x is now what? If I have del L prime by del x, del L prime by del x. So I go to the first equation. I remember at the level of Lagrangian, x prime and x are independent. So the first term, the derivative of the first term is 0. The derivative of the second term in L prime is minus kx. The derivative of the third term is 0. And the derivative of the fourth term is 1. So del L prime by del x is minus kx plus 1. Then I have del L by del X dot. The first term gives mx dot. Second term derivative is 0 with respect to x dot. Fourth term also derivative with respect to x dot is 0. The third term, if I take a derivative with respect to x dot, remember it's a partial derivative with respect to x dot, only t remains, x dot it goes away. So del L by del x dot is mx dot plus t. And when I do a d by dt, it gives me mx double dot plus 1. Now if I write the Lagrangian equation corresponding to this L prime, what I have mx double dot plus 1 equal to minus kx plus 1. 1 and 1 cancel and I get back the same equation mx double dot equal to minus kx. So here I have demonstrated to you with a simple example that I was not trying to fool you using mathematical jargon. It actually is true that if you add d by dt of f of q comma t, it does not change the equation of motion. And to that extent, Lagrangian is not unique. Okay, so let me give a break for a few minutes. I want people to ask because I'm going to go into a slightly different thing now. People can, okay, let me just see if there are any questions. Derivative of del f by del q with respect to time gives only one term. But in next step, how can you write two terms? Okay. No, df by dq, no. Okay. If you write del f by del q, no, in which equation?
Sir, I think participants want to ask question from this page, slide number 5.
Slide number 5.
Right now, okay. Which is on the screen. Yes, sir.
Okay. So del f by del q, he is asking del f by del, okay. Sorry for posting question. Okay. Del f by del q. No, it doesn't give. I mean, I'm just taking. Okay, so let me just quickly say one of them is del L prime by del Q, and there. Del F by del Q. No, there are actually two terms on the right hand side of del L prime. No? L plus del F by del Q Q dot plus del F by del T. Each of these in del F by del Q is also a function of Q and T. Del F by del T is also a function of Q and T. So del F by del Q Q dot, partial derivative with respect to Q, gives me del 2F by del Q square Q dot. And del F by del Q of del F by del T gives me del 2F by del Q del T. Is this the question?
Surendra Kumar Sajan, can you please elaborate your question? Whatever sir has explained right now, is it okay to you?
Okay, yeah, here is it. After derivative, what is it? After derivative of L, what is chat? Okay, after derivative of L
prime, sir, L dash, I think he want to write
with
L
Q
dash?
Dot.
Yeah, with Q dot.
Okay, after derivative. Okay, yeah. Okay, so let us just go to this. So I take del L prime, I take del by del Q dot. So I have del L prime by del Q dot. Next, I have del L by del Q dot. Now, actually, I have two terms here. Okay, but I am doing with respect to Q dot. So the second term, see, F is a function of Q and T. And here I am taking del F by del T, not dF by dt. So there is no Q dot which comes. It is independent of Q dot. So its derivative is 0. Whereas the second term, del F by del Q is independent of Q dot and it is multiplied by Q dot. It is something like d by dx of alpha into x, which is alpha. So del by del Q, Okay, so del by del q dot of del f by del q dot is del f by del q acts as a constant, comes out. Then we have del q dot by del q dot, which is 1. And so you have del f by del q. I don't know if this is correct, if this is what he is asking.
Are you satisfied, Surendra Kumar Sajan? Kindly respond in the chat box.
I think he means the derivative of L dash with Q dot. That is getting dash, is right.
No, the derivative of L dash, no, I understand, with Q dot. So all what I'm saying is in the L prime, there are 3 terms on the right hand side. The last one does not contribute when I do a derivative with respect to Q dot. It becomes 0. Because f is f, and hence del f by del t is not a function of, is only a function of Q and Q dot. It's only a function of Q and T.
Okay, so you move to the next question. And
is it explained now? Sir, after derivative of L with Q dot, that's okay. So that's what I'm saying. After derivative of L with Q dot.
Then further.
Okay, so let me just go through that. Okay, so now I have del f by del Q, and then if I take a d by dt, I will have just a d by dt I have done, and then in the next step I have just split d by dt of del f by del Q as the 2 terms. Because this is a d by dt will have one with respect to Q, the other with respect to Q dot, with respect to T. So I have this. Okay. Okay, fine. Yeah. Any other question? Okay. There are a few of them. Let me just see it here. Derivative of, okay. Sapna, so please repeat L prime equation once again. What is meant by L prime equation? Okay, I will come to that. Sir, would the form of Lagrangian for a quantum mechanical problem be T minus V? Lagrangian has nothing to do with quantum mechanics or classical mechanics. Lagrangian is a Lagrangian is a Lagrangian. What I do with the Lagrangian depends on whether I'm doing classical mechanics or quantum mechanics. Okay, so the Lagrangian will remain T minus V. Although I should say the one thing that when you want to do quantum mechanics, it is not there, because T you generally write as half m x dot square. Whereas when you do quantum mechanics, x dot is not a variable, because x dot implies you know the trajectory. So there you want to convert it into momentum as p square by 2m, only difference. Otherwise, it is still the same. Okay, so you have taken L prime in a different way. Can we take any arbitrary Lagrangian? It may be any complex mathematical function for any function is Lagrangian. Yes. I can take any, I mean, when you say complex, I hope you don't mean complex numbers. I mean, any complicated, you mean. Any complicated mathematical function, as long as it can be written as d by dt of f as a function of q and t, the equations of motion will remain same. Okay. Yeah. Okay. So shall I proceed now? What do you say, Punita? Shall I proceed now? What is?
I think ma'am is not here. Yes, sir, you can proceed.
Okay, fine.
There are no.
There is a time lag. Yes, please go on.
Okay, yeah. So now you come to that mathematical machinery for other problems, which I had said. Next slide or something. Yes. Okay. Can you hear now?
Yes, sir.
Yes.
Because my Bluetooth power is off, so that's why I was asking. Okay, fine. So now the let us.
Sir, your voice is a little bit low now.
Okay. I'll just come near. Is this fine?
Yes, sir.
If you have a problem, then you can shut off your video and keep only the audio on. If there is some
No, it is not a bandwidth problem. It is a problem that my Bluetooth battery is gone over.
Power is off. Okay.
Okay. So now okay. So now look at this Lagrangian principle not as just something which is used for mechanics, but as a mathematical machinery for solving a wider class of problems. The only difference will be, in mechanics, we had said that the Lagrangian is kinetic energy minus potential energy. And we had said, I can choose any Lagrangian and I will get a Lagrangian equation of motion. Whether nature follows that or not is a different issue. But now we find that while the Lagrangian for mechanics was T minus V, this same machinery with different forms of Lagrangian can be used to solve other problems. And as an example, problem of the shape of the soap film. So the problem which I am looking at is the following. I have two rings which are concentric, one of radius R1 and the other of radius R2. Now I take some soap. Now, since because of Corona, everybody will be familiar with soap. So I take some soap and construct a soap film in the region in between, which I have shaded as light blue or gray. Having done this, now this is the top view, so it is horizontally kept. Having done this, I lift the inner ring vertically upwards by a height h. And the problem I pose is, what is the shape taken by the soap film? Now, how do I use this Lagrangian technique which I have developed to solve this problem? Okay. Now, the principle which I follow is this. The film should attain a minimum energy configuration. So this is a general principle in physics, that the most stable configuration for a system is a configuration which is a minimum energy configuration. Now, in the soap film, the surface energy equals the surface tension times the area. Surface tension is basically the surface energy per unit area, which means that if I need to minimize the surface energy, I need to minimize the area. So my problem is now reduced to finding that shape of the film for which the area of the film is minimum, and that will be the shape attained by the film. So now, next page. Okay. So now, roughly, I have just drawn some surface here. Please describe the principle. Okay. The principle is just that any system proceeds towards minimizing its energy. For example, if I leave a ball, it falls down. Why? Because it tries to go to the minimum possible energy it can achieve within the given constraints. So this is a generic principle in physics. This soap film should also try to attain that surface for which the total energy in the film is the minimum. Now, the surface energy of a film is basically the surface tension of the film times the area, which means if the surface energy is to be minimized, the surface area has to be minimized. So it will attain a certain shape which has minimum area. So now we have reduced the problem to a problem of finding out what is the shape for which this film has minimum area. So now let us take an arbitrary shape. But there is one thing which we will use, which will be useful. The two circles, the rings, are concentric, which means if I draw an axis through the centers of the rings, and if I rotate it, it will be perfectly symmetric. In other words, it is cylindrically symmetric, which means it cannot be that the shape of the film is something on one side and something on the other. So I can describe the shape of the film by parameterizing it as, if I take the bigger ring to be at height 0, at a given height, what is the radius of the film? If I give you the height versus radius mapping, I will define completely what is the shape of the film. And so, for such a thing, what is the area? Now, if I take a thin strip, horizontal strip on the film, then the area is 2 pi r is the circumference times the, not the height, but the thickness of the film along the film surface. So it is not dh, but dl. So 2 pi r dl integral over the entire thing is the total area of the film. Now dl I can write it as dr square plus dy square square root. And now I will actually highlight one more thing as we go ahead. Now I can now rewrite this as integral from 0 to h for y, 2 pi r square root of, I take dy square common, so it is 1 plus dr square by dy square times dy. So I have written the area in this form. Now, having written this area in this form, let us try to map it to the action principle. Now, in the action principle, I had a surface area equal to an integral, S is equal to an integral L Q dq by dt t dt. Here I have A equal to a function f, which I will come to what f as a function of r. What is the other thing? dr by dy, which is r prime. And in general, there can be the function y dy. So you see the analogy between these two. What was time has been replaced by y. Oh, see, dl is the length in the slanting direction on the surface. So it is width square, I mean, it is the horizontal thing square plus height square, Pythagoras theorem. And that is why I have dy square plus dr square. Is this clear, Rajiv? Rajiv, is it, sorry, not Rajiv. Manas, yes.
Yes.
Okay.
Yes, sir. Yes, sir.
Okay. So now, so that's how it is. So here I have the correspondence as corresponding to t, that is time in action. I have the height from the ground as y. Corresponding to q, I have r. And corresponding to q dot, which is dq by dt, I have got r prime, which is dr by dy. And corresponding to the Lagrangian L, I have the function f, which is given by 2 pi r square root of 1 plus r prime square. And the corresponding to the action, I have the area. And just like I have to minimize the action, in my problem, I have to minimize the area. So I have completely mapped it. So the mathematics goes completely exactly the way Lagrangian equation goes. In Lagrangian equation, to achieve minimization of action, I have d by dt of del L by del Q dot equal to del L by del Q. And what I have written above, I just replace each one of them one by one. So I have d by dy for d by dt, del f by del r prime for del L by del Q dot equal to, I have del f by del r for del L by del Q. And if I now, sorry.
So hello? It has to be, the handwriting is too small. Poonam, can you just enlarge a bit?
Okay.
150%, 150.
Yeah. Okay.
So move a little bit towards the left, move the paper towards the left. Yes. Yeah, at least, yeah. Okay.
Okay. So now, if I now substitute, so now what is my f? It is 2 pi r square root of 1 plus r prime square. So I dumped this f into this Lagrangian-like equation which is there. So I have d by dy del by del r of r into square root of 1 plus r prime square equal to del by del r of r into square root of 1 plus r prime square. There is a 2 pi factor which will be common on both sides, which will cancel out. And I just solve this and I get in the end the equation r double prime r equal to 1 plus r prime square. This equation is complicated. How do I solve it? Now, I took this example not only to explain how Lagrangian principle, action principle can be used in other areas of physics, but also to demonstrate that from intuition, we have to make a wise choice of variables. Now here I took R as the dependent variable Q and Y as the independent variable which is like T. And I got this equation. Let us now try to interchange the roles and see if I can get a simpler equation. So I go to a next page. Hey, next page. Any questions are there? What is Y? Priyoda Kumar. Okay, Priyoda, the Y is basically the height from the base. The total height is h and Y goes from 0 to h. Just a minute. So you have taken L prime in a different way. Can we take any arbitrary like okay, that already I have answered. Okay. So now let me switch the role of R and Y. So now the same area is A equal to square root of 2 pi r square root of dy square by dr square. Now instead of taking dr outside, I will take instead of taking dy outside the square root, I will take dr outside the square root. So I will have 2 pi r square root of y prime, which is dy by dr, as against dr by dy, which was there, plus 1 dr, which I now write as integral g y comma y prime comma r dr. And now let me see the analogy in a similar way. Now s equal to this thing, a equal to integral g y prime r dr. So here now instead of t it is r, not y, and instead of q it is now y, not instead of q it is now y. So r is the independent variable now. Instead of q dot, which is dq by dt, we now have y prime dy by dr, unlike previously where we had dr by dy. And instead of this Lagrangian L, we now have the function g, which is 2 pi r 1 plus y prime. It should be a square here. Y prime square root. The dr will not be there. I mean, it's just square. Dr is g dr. Okay? And corresponding to x, that will be area. Oh, now I think you will have to again expand it. It may not be easy to see. Okay. So now I have got d by dt del L by del q dot equal to del L. Are there any questions? Is there any, this one, this chat box? Okay. So I have got, okay, so here I have, now instead of del L, instead of d by dy, I have d by dr because r is the independent variable. And I have del g by del y prime, not r prime, equal to del g by del y. Now if I solve this, I will get a much simpler equation, which is r square y prime square equal to a constant times 1 plus y prime square. Now the exercise is to solve it. This can easily be solved. This will actually be a hyperbolic function. And this is the shape of a soap bubble which is trapped between two rings. It will actually, if you can see me, it will come like this. It will be as if, so it's basically r will be a cos hyperbolic function of y. So that is why it was sorry, y will be, yeah, that's how it will be. So there are two reasons why I took this example. One is to demonstrate how action principle can be used in areas other than mechanics, and two, that one has to use your intuition, which comes from practice, to choose the right kind of dependent and independent variables which can make your life simple. I think I'll stop here. Questions, brickbats, criticisms?
The attendees can ask the questions now.
Yes, sir, how can we take out dr from the root in alternate methods? Okay, no, I mean, I can, just like I took dy. I mean, I have square root of dr square plus dy square. I take dr square common. So I have square root of 1 plus y prime square into dr square, and dr square I take out, it becomes dr. The last line on the current slide. Okay. No, there is nothing profound. I mean, I'm basically saying that by using G equivalent to Lagrangian, by using Y as a dependent variable, by using R as an independent variable, I put it in the Lagrangian equation which I have written for this, and I solve this. I will in the end get this one, this equation. I just have, I mean, you have to solve that. This is just straightforward differential equation solving. See, okay. See, remember, can we have more such problem? Okay, let me see. Okay. Now, see, the interesting thing is the following. Thanks here. I mean, yeah, okay. So, the interesting thing is the following. Why is it that this became simpler? If you take the previous method had the dependent variable as well as the derivative of the dependent variable inside the function f. Whereas when I use g, then in g, there is only y prime. Y does not appear. And that is why the right-hand side of the Lagrangian equation becomes 0. And thus, simplifying your life. Del g by del y is 0. And that, so these are the kind of things which one should inspect to select a judicious form of independent and dependent variable. More questions?
Yes, sir. One more question by Gitansh Arora in the Q&A section.
Is the property that the Lagrangian isn't unique useful in a situation? Yes, it is. Okay. I will tell you where it is useful. Okay, maybe I'll tell you tomorrow, because basically, usually one says that if Lagrangian has an explicit function of time, then energy is not conserved. It is like if suppose potential is a function of time, then energy will not be conserved. But one has to be careful that this time dependence may be high, may be there in this form when such a situation does not happen. But I will try to construct some more examples and give you during the course of these lectures. Don't praise me so much here, I may believe it. Okay?
Have to believe it. I'm getting goosebumps ever since your lecture has started, Sesh. Right. So I was having really goosebumps, I was sitting as a first year BSc student once again in classical mechanics class. The class, it was wonderful. It was simply wonderful. I mean, I don't know how people find it, but I found it amazing, because very, very few people point out these very details which comes after, diving deep into any subject,
Yeah, that is right. I mean, when I was doing MSc, I was also like any other person. I was based by classical mechanics, As a Lagrangian means kinetic energy minus potential energy, never knew why it means. I mean, progress is always the next generation should be better than the previous one. And so the next generation teach the previous generation should teach the next generation what it has learned.
Yes,
Sir,
indeed,
one more
indeed.
question is waiting in the Q&A box by Pranjali Sharma.
Okay. If Lagrangian and Newtonian mechanics they are not independent, what she means is not independent, then what is the advantage of using them? Okay, fine, good. Okay. Now, what happens is, it is often easier to calculate potential energy than actually calculate the detailed force on a system. For example, suppose you are, so suppose there is a road on the side or on a hill, and the road is ups and downs. Now, at any point, I can easily calculate the potential energy, just a total height from the top or total height from the bottom. Whereas if I want to calculate the force, I have to take what direction and all those things. Okay, so this is a simple example where basically it is mathematically, it is often easy to formulate what is the potential energy than actually calculate what is the force. Chat box. Okay, sir. Yes, boss.
No other questions, only appreciations in the chat.
And you don't appreciate so much.
You only appreciate. You only
starts,
Sir, you deserve
it. Now I'm thinking, why did I ask you for only few lectures? I should have asked you for a month-long lecture, you know.
Yes, but that's what I want to say. I have revised my classical mechanics, just scrolling down and up the screen. I mean the sheets. I have just revised.
So you can, so what all will you be teaching us? You can tell that. The students are asking, will we have more lectures like this? I said, yes, I've requested sir enough to...
so what I will do is, okay, so tomorrow I will take this, tomorrow I will tell a very interesting thing about, as I was saying, there are very few problems which can be solved exactly. For example, simple harmonic oscillator is a problem which can be solved exactly. Now, suppose I have a potential which is not x square, but it is x to the power 4. Now, it can't be solved exactly, but one can ask the question, is everything lost? Can I not know anything about the system? The answer is, there's a lot of information you can know about the system, and that is goes by the name of scaling relationships. So I will take, which basically means if you have a potential, which is a power law in position, then what you can know about, say, time period of the system. Okay, that is what it is. Yeah, what about the x to power n? That's what. And I will use this to tell you, using this simple thing, we can figure out the Kepler's third law of motion. Why is it that t square, the time square of the orbital time period is cube of the semi-major axis? Okay, we can derive all that from there. I will go over that. And at some point, I will also talk about Hamiltonian. Now, again, there, I will like to spend some time on a subtlety. Often they say Hamiltonian and they will say that Legendre transformation. And you have come across Legendre transformation when you go from Hamiltonian to Lagrangian. The same this transformation you do in thermodynamics when you go from internal energy to enthalpy. Again, okay, Brachiostrand problem I will highlight. Yeah, okay. Again, when you go from Gibbs free energy to enthalpy, and they are not different. They are all under the same mathematical structure called Legendre transformation. And I will not go into too much of detail, but I will give you a flavor of what is at the root of this Legendre transformation. That is, when I define Gibbs free energy from enthalpy or Hamiltonian from energy, what exactly happens, that I will go over.
So, okay. So then we look forward to all your lectures and request you to grant us more and more lectures.
Oh, okay.
Okay. So it was indeed a pleasure, and I along with the attendees and Nasi and my co-convener and organizing.
It's a great pleasure. What happens is at home they say that if I don't have an opportunity to give gyan to somebody, I feel very sad. So whenever I'm discussing something at home, my mother keeps reminding me, please remember that you're talking in house and you're not giving a lecture to your students. Okay.
I think that's a problem with all teachers,
Yes.
With all teachers. So thank you, Professor Seshadri, and we look forward to your lecture tomorrow evening.
Thanks.
Okay. Thank you very much.
Professor Seshadri. It was indeed a very good talk. Thank you so much.
Okay.
Okay, so we have now our next.
Thank you so much, sir.
Thank you.
Thank you. Yeah.
Ma'am, just give me 1 minute so that I can stop the recording and restart.
Yeah, please. We would just for a fraction of a second, we stop and we start again.
Yes.
And with that, and I request Dr. Sudha Gulati to meanwhile